Imagine you're coding a smart irrigation controller with soil sensors, Wi-Fi logging, and a pump relay. If you put everything inside one giant while loop, sooner or later something breaks, Wi-Fi times out, sensor values get missed, or the pump doesn't turn on in time. Microcontrollers can only do one thing at a time, so without structure, important tasks compete for CPU and fail unpredictably. This is why multitasking is critical in modern IoT devices. FreeRTOS, built into ESP-IDF, gives you a way to split your firmware into independent workers called tasks, each with priorities and timing rules. Instead of juggling dozens of delays, you let the scheduler orchestrate who runs when. By the end of this module, you'll know how to design firmware that feels smooth, responsive, and professional, even when your ESP32 is running multiple jobs at once. A task in FreeRTOS is like a worker hired for a specific job inside your ESP32. Each task runs a function repeatedly, has its own memory stack, and operates independently of others. For example, one task may blink an LED for system health, another may maintain an MQTT connection, and a third may handle sensor reads. You don't have to micromanage who runs first. The FreeRTOS scheduler does that. But here's the key. Tasks are cooperative. If a task never yields or delays, it hogs the CPU and starves others. That's why tasks should either finish quickly, call task delay, or wait on events. The art of multitasking isn't creating dozens of tasks, but knowing when a job deserves its own independent worker versus being grouped with another. This makes your firmware modular, debuggable, and much closer to production quality. Priorities decide who gets CPU time when multiple tasks are ready. Think of it like seating in a busy restaurant. VIPs get served first, while regular guests wait. In FreeRTOS, a high priority task always preempts a lower one. This is powerful but dangerous. If you set everything to high priority, the CPU will collapse. Good design means carefully ranking tasks. Wi-Fi or safety-critical control loops usually deserve higher priority, while background logging or LED blinking can stay low. Tasks with equal priority share CPU time in a round-robin manner, which ensures fairness. The big picture is balance. You don't want sensor updates to be starved by long MQTT retries, nor do you want Wi-Fi to drop just because an LED blinks too frequently. By assigning priorities thoughtfully, you can keep every subsystem responsive without unnecessary resets or instability. This is where many Arduino users stumble. In Arduino, delay 1000 freezes the CPU for 1 second. Nothing else happens during that time. In FreeRTOS, the smarter way is vtask delay. Instead of blocking, it tells the scheduler, I don't need CPU for X milliseconds, let someone else run. This keeps the system alive and responsive. Similarly, task yield lets a task voluntarily hand over control even sooner. Without these tools, one task may dominate the CPU and make your firmware look hung, even though code is running. The secret is balance. Use small, well-placed delays that match the natural rhythm of your tasks. For example, a soil sensor might only need checking every 2 seconds, while Wi-Fi may need frequent attention. Proper yielding ensures every task gets its fair share of CPU without wasteful blocking. Let's break down scheduler behavior with a simple table. Imagine 3 tasks running: Wi-Fi, priority 3, sensor RAID, priority 2, and LED blink, priority 1. If Wi-Fi and sensor are both ready, Wi-Fi always runs first. When Wi-Fi waits or yields, the sensor task runs. The LED, being lowest, only runs when nothing else is ready. If 2 tasks share the same priority, the scheduler alternates between them in equal slices. Tasks that call vtask delay move into a blocked state until their time expires, making room for others. Finally, if nothing is running, the idle task executes in the background. Understanding this flow helps you predict system performance and avoid surprises. It's like an orchestra. The conductor, scheduler, decides who plays when, so the music, your firmware, never falls apart. Each task in FreeRTOS has its own stack. Think of a stack like a backpack that the worker carries, too small and it overflows, causing crashes, too large and it wastes RAM. Beginners often underestimate stack size, leading to random reboots or hard faults. Always estimate memory needs based on what the task does. Wi-Fi tasks need much more than an LED blink. Use FreeRTOS stack monitoring tools, task get stack high watermark, to check how close you are to overflow. Also, remember, more tasks is equal to more stacks, which consumes RAM fast. On the ESP32, with limited memory, you must strike a balance between parallelism and efficiency. Good engineers design tasks to be lean, allocate stack sizes carefully, and rely on inter-task communication instead of spinning up endless new tasks. Many FreeRTOS projects fail due to beginner mistakes. The first trap is using Arduino-style delay inside tasks, which locks the scheduler. The second is creating too many tasks. Each consumes memory and increases context switching. Third, improper stack sizing often causes mystery crashes that are actually memory overflows. Another mistake is assigning every task high priority, which starves others. Finally, neglecting inter-task communication leads to clunky polling loops instead of smooth message passing. The fix is discipline. Keep tasks minimal, yield properly, size stacks carefully, and use queues or semaphores for communication. Think of the scheduler as your project manager. Respect its rules, and your system will remain stable. Abuse them, and everything spirals out of control. We've covered the essentials of multitasking with FreeRTOS on the ESP32. You now understand what tasks are, how priorities control execution, and why delays and yielding are crucial for responsiveness. You've seen how the scheduler behaves, why stack management matters, and the pitfalls to avoid. At this point, you should stop thinking of ESP32 code as a single endless loop and start thinking of it as a team of workers, each with a role and priority. This mental shift is the foundation of professional-grade IoT firmware. In the next hands-on lessons, you'll practice creating tasks, experimenting with priorities, and testing the effects of V-task delay. Once you've mastered these basics, you'll be ready to explore inter-task communication with queues and semaphores, the real secret to scaling up complex systems.